Welcome students, welcome back to this lecture series on VLSI design KEC 072. This is lecture number 12, I am Dr. Raman Kapoor. So, today we will be continuing our discussion related to dynamic CMOS logic circuits. In the previous class, we have completed how dynamic CMOS circuit design and working works, how a dynamic CMOS circuit differs from a static CMOS circuit. Just to summarize, a dynamic CMOS circuit has two distinct stages of operation, number 1 being pre-charge and number 2 being evaluation. As compared to any static CMOS circuit, a dynamic CMOS circuit involves the use of clock. So, when the clock goes low or logic 0, the pre-charge state works, it comes into action and the output capacitor or a load capacitor charges to the power supply VDD. Okay. So, your output goes to logic 1 during pre-charging when clock is low. When the clock changes its polarity, when it goes high, the evaluation stage kicks in and whatever logic you are trying to implement, that logic is tested and the output is connected to the load capacitor. Now, in the evaluation stage, either the output can make a transition from 1 to 0 or stay at logic 1. Okay. So, this way a dynamic CMOS circuit basically allows you to have lesser number of transistors for the same logic operation as compared to static CMOS circuit. Now, this advantage is used for improving or utilizing the complexity of a circuit. For complex circuits with large functionality, we need a very complex circuit diagram, a complex circuit arrangement, and dynamic CMOS tends to help us in that way. But the way we implement it, cascading is a very common approach whenever the circuit complexity has to be increased or functionality has to be enhanced. But when it comes to dynamic CMOS circuit, cascading does not work in a simple way. It is not as simple as connecting the output of the first stage to the input of the second stage. Okay. So, if you do that, if you do a simple series connection, it is possible that the signal strength will be reduced, noise margins will be affected and overall you might see a malfunctioning such that the output become erroneous. Let us see one example here. The circuit diagram shown to you is a simple cascaded connection, or you can say a simple series connection of two dynamic CMOS inverters. So, the circuit on the left has been directly connected to the circuit on the right by a simple piece of wire. Okay. So, the output of the first stage, which is labeled as out 1, is connected as input to the second stage. You can make out that this is a dynamic CMOS circuit. You have a pre-charge transistor connected to the clock. The same clock is connected to the evaluation transistor. Okay. So, during pre-charging your out goes high and during evaluation the logic of this input is tested, right. So, let us see how this circuit works. On the right we are also seeing the timing diagram. So, you have the clock at the top, you have the primary input in, the output of stage 1 and the output of stage 2. Okay. When clock is low, this is your evaluation stage. Okay. This output 1, output load capacitor, this you can call it C1, this charges to VDD. Okay. So, out 1 goes to logic 1, right. This is after the pre-charge state. Suppose the primary input, I am calling it primary input because it is the original input which is being initially applied to the first stage. Okay. In a cascaded connection, the very first input you are applying is basically considered as your primary input. Suppose this primary input makes a transition from 0 to 1, like here, it is 0 here and then it goes to logic 1. Now, when this goes to logic 1 and clock is also high, the evaluation transistor is on and this transistor, the logic is also on. Okay. So, the out 1, the capacitor at out 1, the load capacitor has a path to discharge towards ground. So, out 1 starts to discharge from 1 to 0, which we can see here, this discharging effect you can see here. till here it is okay. But now this signal is acting as input to this stage. When clock is 1, they are sharing the same clock. This PMOS is off, this evaluation transistor is on. If this is discharging, if out 1 is discharging, this transistor should be off. Okay. So, out 2 should hold its output, which is logic 1, but what happens that every logic gate and especially dynamic circuits, they work on the principle of capacitive charging and discharging. For holding of data, you need continuous refreshing, or at least a path should be disallowed for discharging, so that charge can be held. Okay. But in this case, because of the finite propagation delays, this discharging at out 1 from 1 to 0 takes a finite amount of time. Until this discharges to the threshold 2 or below the threshold voltage of this NMOS transistor, you are having logic 1 at the input of this transistor, okay, which means until the stage 1 output discharges to a value equal to or lower than the threshold of the second NMOS transistor, second logic NMOS transistor, so this one, until then this transistor will be on. Because of that, when this is on, out 2 also begins to discharge via ground. Okay. So, this starts to lose charge here, and as soon as the threshold is exceeded on the downside, this transistor goes off and there is no path to discharge. So, some loss of charge is experienced. Okay. So, what we are seeing here, we have connected two very simple dynamic CMOS circuit, two dynamic CMOS inverters directly in series via a wire, okay, a simple piece of wire connecting the output of stage 1 to the input of stage 2. And what it does is that due to finite delays of any switching circuit, any logic circuit, charge loss is taking place, and now this charge cannot be retrieved, because you again have to first go through the pre-charge cycle again, you have to wait for the clock to go low again. If it is an asynchronous circuit which is low for a small period of time and high for a large period of time, then the charging cycle is again going to take a large amount of time. And for that time duration, for a very finite time duration, the charge on the second output, out 2 here, is lost. Now, this is giving us erroneous output. Out 1 should have discharged, that is expected, but out 2 should have held its value 1. Okay. So, this basically tells us that simple cascading connection between two dynamic CMOS circuits is not going to allow us the advantage of a dynamic circuit which is increased complexity. Okay. Now, if I want to implement a highly complex circuit using dynamic CMOS logic, simple cascading connection will not work. Okay. So, this is a problem, this is a major problem which does not happen in static CMOS circuit, because their data is held as long as your power is on. So, there is a lot of time period is there which can cover the propagation delays. So, data integrity is not affected, but in dynamic CMOS circuit, because of this continuous charging, discharging and finite time it takes to do that, the simple cascading will definitely cause loss of charge, loss of valuable data, which again cannot be retrieved within the evaluation cycle. Okay. So, cascading problem arises because the outputs of each gate, they have been charged to 1. We know when the clock goes low, the PMOS, the evaluation transistor turns on, and that charges the output load capacitor to VDD. Okay. So, all the stages, even if you have n number of stages, every stage will be pre-charged to high logic, logic 1 when pre-charge cycle comes. Now, because of this, because there is by default you have logic 1 at the output in any dynamic CMOS circuit, the only transition it can make is from 1 to 0. Okay. If it remains at 1, it is holding the charge, that is not a transition. The only transition it makes it from 1 to 0, and that lost charge cannot be retrieved. So, this problem has a solution in itself, that instead of pre-charging to 1, if you leave the stage 1 and for all subsequent stages which are being connected in cascade, if somehow you can make the inputs after pre-charge equal to 0. That will to a great extent address this problem of cascading. A common approach of solving this problem of cascading is what is known as domino logic. Okay. Domino logic offers a very simple technique. It helps in avoiding this problem of charge loss due to simple cascading. Okay. It uses single clock as before. So, every stage is using the same clock, they are synchronized to the same clock period. A dynamic logic module has a small difference, that between successive stages, if I call this as stage 1 and stage 2, you can have multiple stages. Instead of directly connecting, I am going to use an inverter. Okay. So, I am going to use an inverter to produce a cascaded connection between two successive dynamic CMOS circuits. Okay. Everything else remains same. You have a PMOS pre-charging transistor, you have an NMOS evaluation transistor, both sharing same clock. You have a pull down network consisting of NMOS. Okay. So, this is going to have NMOS network and this is going to have a PMOS network. Okay. The pull down network consisting of PMOS and a pull up network consisting of NMOS circuits. So, if you look at stage number 1, when clock goes low, this point here is going to pre-charge to 1, this point here is going to pre-charge to 1. But for every successive stage, because of this inverter, the input which is being passed on is actually a 0. Okay. So, you can have n number of successive stages following after the first stage, just place an inverter in the middle, so that when the pre-charging cycle ends, the input at each of the successive stages of a cascaded connection is actually 0, but not equal to 1. Okay. So, this is slightly different from the standard dynamic CMOS circuit, where by default after pre-charging you have 1 present at the output. Either you hold that 1 or you make a transition from 1 to 0. But here in this case, we are connecting an inverter to allow cascading connection, such that after your pre-charge has ended, every input of the successive stage after the first stage is actually having a 0, okay, after pre-charging. So, now basically when you have 0 at the input, before the evaluation starts, there is no charge to be lost. Okay. The problem of cascading was that charge was getting lost. Logic 1 was discharging towards logic 0, but now you have eliminated that, you do not have any charge to lose here. Okay. So, if you have 0 by default, you can either charge to 1, which is a transition which is based on logic which you are testing, or you keep a 0. There is no point, there is no possibility of losing a charge, because you actually do not have any charge present to start with. Okay. So, now the evaluation stage works as it is. When the clock goes high, evaluation transistor goes on, this evaluation transistor goes on, pre-charge transistors go off, there is a 0 here. Okay. So, until and unless your logic 1, your input, this say in 4 here, if it is not providing a path, there is not going to be any discharge, okay, and 1 is going to be remain. If somehow it provides a path to discharge, then a 0 is going to remain. Okay. And then evaluation is done for every successive stage, and when the pre-charge comes again by default you have input as 0. Okay. So, this is known as domino. The word domino is coming from the fact is that if you have a large collection of dominoes, and if you apply a small energy to the first domino, it creates a cascading effect where one makes another one fall, the second one leads to a fall in third one, and so on, the so called domino effect. So, from stage 2 onwards, a domino effect is taking place, such that logic 0 is getting propagated like a domino. Okay. That is why this name is used. The only difference between a standard dynamic CMOS circuit and a domino logic circuit is the presence of this inverter between stage 1 and stage 2. This is again a brief summary of the working which I have just explained. So, during pre-charge, the output of the n type dynamic gate is charged up to VDD, the standard procedure, and the output of inverter is set to 0. Okay. And during evaluation, depending upon the logic which you are testing, conditionally your gate can discharge. Well, there is nothing to discharge, okay, because it is already logic 0 at the input. Okay. Either it can discharge or the output of the inverter can make a conditional transition from 0 to 1. So, that is the only possible transition left. Okay. So, this to some extent or to a great extent we can say solves the problem of cascading. The charge loss which takes place when we are connecting a simple cascaded circuit is solved by connecting this inverter between two successive stages. Okay. So, this basically domino logic connection ensures that all inputs to the next logic block are set to 0 okay, after the pre-charge. The only possible transition you can have is that of a charging. Okay. So, either you can add the charge or you can just stay at the ground potential. Okay. This transition can affect the next domino and so on, like a domino effect which I have just explained. Okay. Let us see some of the features. Right. So, this is the first line which you read here, that each domino logic gate is going to require n plus 4 transistors. Here n is the number of inputs. Okay. It is those inputs which you have applied to your pull down network for evaluation, conditional evaluation. Okay. So, the one of the advantage of dynamic CMOS circuit was that it requires less number of transistors, but to solve this problem of cascade we have to connect some extra number of transistors, but not as high as you would need in a static circuit. Okay. So, that advantage to some extent still remains, but the area required, the density of circuitry tends to go up slightly. And why n plus 4? If you see this circuit here, here you have 3 inputs. Okay. So, I can say n is 3, right, 3 input circuit. I connect one pre-charge transistor, I connect one evaluation transistor. Okay. So, it becomes n plus pre-charge plus evaluation, plus for this inverter you need one PMOS and one NMOS. Okay. So, every 1 bit inverter you need 2 transistors. So, this basically gives me n plus 4 transistors. Okay. So, every domino logic circuit is going to, at least for every bit of operation, it is going to increase the number of transistors by 4. Okay. Logic evaluation propagates itself as a falling domino effect. Okay. So, minimum evaluation period is determined by the depth of logic, by the number of the number of logic inputs you have, the complexity of the pull down network for evaluation you have, that is what logic depth is. Okay. Domino gates can be made more immune to parasitic effects by adding a level restoring transistor to the static CMOS inverter. Okay. Well, that is not something which is critical to the operation, okay. But if you want to reduce parasitic effects, you can add another transistor, but that is extra circuitry. If it is very necessary, then you can go for it. Now, what is the effect of adding this inverter at the output of stage 1, okay, or for every preceding stage you are adding an inverter at the output? What it does is that it results in a low impedance output which increases noise immunity. See, one of the major difference between a static circuit and a dynamic circuit was static circuits have better noise immunity, okay, because even if you have higher noise environment, the output remains stable for more amount of time, right, in a static circuit. So, when you have added a static inverter in the middle, you are actually increasing the noise immunity, okay, and you are providing a low impedance output because the output itself is logic 0. Reduces the capacitance of the dynamic output node by separating internal and load capacitances. Okay. It allows optimization of fan out for high speed operation, okay. And the output of a domino logic family is non inverting. Right. Now, this is a sort of an issue from the design aspect. The universal logic gates are NAND and NOR, which are inverting in nature. When we do any CMOS design, we basically are designing an inverting logic circuit. So, you first design the NMOS circuit pull down network using your NAND or NOR gates using inverting logic, and then use a complementary version of that in the PMOS circuit. So, if you have a series connection in the pull down network, you would replace it with a parallel network in the pull up side and vice versa. Okay. Since you are connecting an inverter at the output for domino logic, in that case you are basically inverting the output at every stage, and since the design by default was inverting, after connecting this inverter you are basically producing a non-inverting circuit. This can be an issue from the scalability point of view, right, because if a setup is already ready for an inverting technology, to produce a non-inverting output and then probably at some other stage inverting it again is a cost and scalability issue. Okay. So, this is one of the issue which is associated with domino logic, that the output is actually non-inverting when most of the CMOS logic design is a inverting design. How we can to some extent solve this problem, okay, is what is known as a inverting domino logic. Okay. This is one circuit, this is not the only circuit which is going to solve this problem of inversion and non-inversion, but this is one of the circuit which we can look at or consider. Okay. So, as said, a major limitation is to produce inverting logic functions. What we use is a dual rail domino. What does dual rail mean? Dual rail basically means that at any point there are going to be two sets of wires. Okay. So, there are going to be two wires. Okay. One of the wire is going to give you logic high output. Okay. So, output of one of the wire is going to be 1 when the signal which is feeding that wire is also 1. Okay. So, suppose a wire is being fed by input A, when input A goes 1, you get a 1 at the output, and then there is going to be another set of wire such that when A bar goes 1, then also it shows you output 1. Okay. So, two wires, that is why it is called dual rail. One of the wire is going to give logic high output when the signal driving it is true. The second wire is also going to give you a high logic output when the signal driving it is false. You can consider it as active low and active high signals. Okay. And the signal connection is what is known as a cross coupled differential circuit. Okay. A differential circuit is one which is also complementary in nature, so that one part of the circuit runs under certain condition and the another part of the circuit works when the conditions are complementary. Okay. Like NMOS and PMOS are complementary to each other, something like that we are using a differential circuit. Okay. So, DCVS or differential cascade voltage switch you may have read before in some other sources. What it basically means that it uses cross coupled PMOS circuits. Okay. This which you see in gray in the middle, this is optional, this part is optional, this is only used for increasing the duration of your pre-charge, okay, for allowing the charge to be valid for a longer time even if your pre-charge cycle is less. So, okay. So, this cross coupled connection basically extends that pre-charge cycle. This is optional. The inverting logic can be implemented if you do not have this here, okay. It can still be implemented, but this has an extra benefit of enhancing your pre-charge cycle. So, from this PMOS side, this PMOS and this PMOS, they are cross coupled such that the output of this segment is connected to this PMOS and the output of this segment is connected to this PMOS, and all the 4 types of inputs are available. By 4 I mean A is here, A bar is here, B is here and B bar is here, okay, which means both true and complementary inputs are available, and because of this cross coupled connection both the outputs are also available. Okay. So, if we are suppose implementing an AND gate, a simple domino logic is going to be non-inverting, it is going to give you A dot B. Okay. If you want the complement of it, that is what you are going to get from this end. So, this cross coupled differential connection, okay, with this circuit in the middle for extended pre-charge time, okay, it is going to provide you both inverting and non-inverting outputs, and it is going to accept both inverting and non-inverting inputs. Okay. That is why it is known as a dual rail domino logic, also known as a differential cascade voltage switch. So, this kind of a cross coupling from the output of one stage to the Pmos of second stage and the output of second stage to the Pmos of preceding stage, this cross coupling differential connection provides you both complementary and non-complementary outputs. So, the problem which we had of producing non-inverting logic from a domino circuit, that is resolved, and with this circuit you solve the problem of cascading. Okay. Charge loss is prevented because you are using domino circuit, and cross coupling allows you both inverting and non-inverting outputs. Okay. So, this is how you can obtain inverting domino logic. Okay. So, just to summarize, we have discussed the issue of cascading in dynamic CMOS circuits. You cannot simply connect stage 1 to stage 2. You need, for a domino logic circuit, which is one of the solution to this problem, is to connect an inverter between successive stages. Okay. That solves the problem of charge loss, because by default every input which you are propagating is a logic 0. So, there is no charge to be lost. It produces a small issue that you will only obtain non-inverting logics. Okay. To solve that, you can use a cross coupled dual rail network which produces both complementary and non-complementary outputs. So, this was a discussion on cascading in dynamic circuits and implementation of domino logic. Thank you.